Presented by Caltech.
So welcome to the Watson Lecture. I'm Kerry Vahala, and I'm the Executive Officer of the Department of Applied Physics and Material Science at Caltech, the department in which Kathy Faber conducts her research. Kathy is the Simon Ramo Professor of Material Science, and as probably many of you know, she recently joined the faculty at Caltech just in the last year. Previously, she was at Northwestern University, where she was also in the Department of Material Science. And at Northwestern, besides the research that she does in teaching, she's also held several leadership positions. She was the Dean for Graduate Studies and Research, and before that was also the chair of the Department of Material Science and Engineering. Kathy's received many awards and honors over the years, and one I'll just mention that she received last year. She was elected to the American Academy of Arts and Sciences. Now, the work that Kathy does and the research that we'll hear about tonight is generally part of the broad area of material science. A number of different faculty involved in this area at Caltech. And Kathy's unique area of specialization is in high-performance ceramics. And my own area is something quite different, but over the last year, I've had a chance to become more and more familiar with the kind of work that goes on in this subject and the actual research that Kathy is involved with. And we'll hear about one facet of that tonight, but I thought I would mention that in addition to what you'll hear tonight, Kathy has many other areas. One of them that I'm particularly interested in, and I've had a chance to learn about over the last year, is the application of ceramics, and perhaps some of you know about this, to actually jet aircraft engines. And there's been a push, obviously, to drive the efficiency of these engines to higher levels. And scientifically, the principle that guides us in that is to try to make the engines operate at higher temperatures. The law of thermodynamics are in effect here, the Carnot efficiency. And essentially, that has a limit, and the limit is set by the material properties. And so it turns out that ceramics are used actually to increase the durability of the turbine blades, okay, which are whirling around at tremendous speeds and at ever higher temperatures in these jet aircraft engines. And this is another area that Kathy is involved with. Now, tonight, okay, we're going to hear about something completely different. Another area, okay, that involves material science, but now the connection is to the art world. Kathy, as it turns out, is a leader and pioneer in this area. This is something she started when she was at Northwestern University, and she formed and is still the co-director of the Center for Scientific Studies in the Arts in Chicago, and that's a partnership between the Northwestern University and the Art Institute of Chicago. And basically the focus of that center is on the study of art conservation, okay, what we'll hear about tonight. So the title of Kathy's talk, okay, is Watching Paint Dry and Colors Fade. And so please join me in welcoming Professor Faber.
Thank you very much. Thanks for joining me here this evening to talk about art and science. And I especially like this juxtaposition of Pablo Picasso's red armchair here. You may love it, you may hate it, but you have an emotional response to that particular painting. And I use this as the start of my presentation because it brings to the fore what happens. Why do we take a beautiful work of art and turn it into an object of science inquiry? And so I would like to do that this evening with a number of examples. I first got involved in this more than a dozen years ago, quite serendipitously. And what I learned very quickly is that there is a lot of science that goes on in a museum, at least in the major museums around the world. And to give you a sense of that, I've put this slide together with all the many scientific aspects of museum research. Perhaps the most common nowadays is that of technical art history, in which we learn as much as we possibly can about an object to better explain history, and that includes the history of the object itself. So for example, if we were to find out some of the minor constituents in a paint or in a ceramic body shown here, we might be able to say something about trade routes in the processing of that material that took place. By knowing an awful lot about the technical art history of materials, that can aid us in treating them. And so we can, once we understand the materials, we might know better how to correct any damage that has occurred. Of course, we are often interested in provenance of materials, whether or not an object is correctly attributed to a specific artist. In a crass way, we'd say we're looking out for fakes, but we won't use that term anymore tonight. And another aspect has to do with what we call sub-nanogram analyte sensing, looking for very, very small quantities. And the example that I'm going to provide tonight actually then takes us to virtual restoration. And before I leave this slide, I wanted to mention one other aspect, and that is non-destructive testing. The conservation science community can benefit a great deal from non-invasive and non-destructive techniques. And in fact, the reason I wanted to bring this up is because our colleagues up at the Jet Propulsion Lab developed a portable X-ray diffractometer. I think it is in operation on Curiosity right now. And delightfully, the Getty also has one, so that they can take it into museums and do some non-destructive evaluation. So let me just spend a couple of minutes talking about museum laboratories and their history. In Europe, the very first museum laboratory was in Berlin. And Friedrich Rothgen here is really known as the father of conservation science. So that was back in the 1800s. When we moved to the 20th century, there was a laboratory established in London, at the British Museum, the National Gallery, and in the Louvre. And these are all photographs of the directors of those laboratories. In the United States, the first laboratory was actually at the Strauss Center for Conservation at Harvard. And this is a photograph of the new Harvard Art Museum and their conservation lab. Of course, down the road here, there's a phenomenal facility at the Getty Conservation Institute. There's one at the Met and the National Gallery. And the numbers that I've placed in here, 3, 25, 15, and 10, are the number of conservation scientists that are in those specific labs. If I were to take all of those numbers from all of the museum laboratories around the country, I would come up with a number no greater than about 175. Only 175 PhD level scientists working in museums. How many museums are there in this country? About, one source I read said 17,500, okay? What this means is that this is a fantastic opportunity for those of us in universities, if we can make the right links. And so that is what happened to me about 12 years ago with the very first conservation scientist at the Art Institute of Chicago. This is Francesca Casadillo, an extraordinary individual. And we partnered initially, we partnered when she came to the Art Institute. We studied their collection. I identified other engineers and scientists within Northwestern to also work on the collection. And about 2.5 years ago, we decided to get bigger and better and formed our Center for Scientific Studies in the Arts, which has allowed us to continue to study cultural heritage objects, to develop new tools, to study degradation and improve conservation strategies. But through the support of the Mellon Foundation and through our center, we also are able to invite other museums into Northwestern to study their own collections. So this is a way of addressing some of those, 16,999 museums that don't have scientific staff. And hopefully this will ultimately bridge the scientific conservation communities. So let me just back up for a second. What I want to do this evening is provide you with 5 examples of the work that we have done through the years and addressing these circled areas. So I'm going to give 2 examples in technical art history, one in treatment. The red armchair has not been treated, but in fact the work there was an inspiration for us to do some studies that will influence treatment, the provenance and the subnanogram analyte. So let's move forward then and look at some of these examples. So the first is going back to Picasso. And here he is. Here is the master over here. And you look at this photograph, and of course, the normal, everyday person looks at what he's painting. If you're a scientist, you look at the paint can, okay? And Picasso was, in his time, this was painted in the 30s, was pushing the limit. And so he decided to use house paints. And in France at the time, the most famous and most reliable source of house paints was a company by the name of Ripolin. And you can see some of the Ripolin cans here. The question that came to us from the technical art history standpoint was, if we look at a Picasso, do we know which of his paints are house paints and which are traditional artist's oil tube paints? And how easily is that to figure out? Well, as you can tell, it was figured out. This is a cartoon that I just love that was in the New York Times Magazine after the work. The work was published and then appeared in the Times, and here is our house painter working on the red armchair. One point that I should bring up here has to do with house paints. In France, lead was prohibited in paints as early as 1909. So there had to be a shift then in the formulations for paint at the time. So that comes into play here as we explore the materials. And there was an arsenal of techniques that was brought forward for this particular project, a lot of analytical chemistry techniques, a lot of spectroscopy techniques, but the only one I'm going to talk about tonight has to do with that was accomplished at the Advanced Photon Source at Argonne National Laboratory, where a spectrometer could be used to look at X-ray fluorescence, but it could be done at the scale in which one could examine the impurities in a single grain of pigment. And so on the left here is an electron micrograph of a couple of white paints. Here is the Ripplein paint, and here is a Lafranc zinc white artist tube paint. And you can see that morphologically they're very different. There are large pigment particles here compared to these small ones. But it's only when you get to look at the elemental signature at the nanoscale that one can see the differences. So here we see in the Ripplein paint the strong zinc signature. That is now the pigment as opposed to lead. We see that basically the lead is gone. It's not very bright here. It's really the zinc signal that is prominent. There's a little bit of iron, a little bit of titanium. In contrast, it was in the tube paint here, we do see a zinc signature, but there's also evidence here of lead still in these artist paints in the 30s. So with this combination of microscopy and spectroscopy techniques, we're now able to look at Picasso's paints and pick out the various areas on a specific painting that are house paints. Now, I said that this inspired us to do further work, and this is where we watch paint dry. And so in our laboratory, we are now making some model paints, and those include zinc oxide, so that's the pigment, into some very simple synthetic oils. And the reason we want to do that is because in the lifetime of a paint, there are a lot of changes. So all of you have probably done some painting. When you start the process and dip that paintbrush into the jar of paint, you see a substance that looks like this. We describe that behavior as viscoelastic. And what I mean by that, it's I guess one way to think about it, it's like honey, but it has some spring back, if you will. It's got both viscous qualities and elastic qualities. But through its lifetime, as solvents come off, as the structure of the paint develops, we go from this viscoelastic solid to a brittle solid. And you can see here that Mona Lisa, at 500 years old now, her complexion has really degraded. And so these are actual cracks in the paint. And so what we want to be able to do is study that. And in the laboratory, the way that is done is with two techniques. The first technique is called a quartz crystal microbalance. It's a very, very sensitive balance, so we can monitor mass, but we also, in that technique, are sending a shear wave through the solid, and it gives us an indication of the stiffness of the material. And so through that, what we're monitoring here is the mass, and we see that in very early stages, in seconds in fact, the solvent in this paint is now beginning to evaporate, so the mass decreases, and then things turn around. And that's because these paints are reacting with the atmosphere. This is called an oxidative reaction, and that reaction is forming a very rigid paint. And we can follow that here with this increase in mass, and then eventually some of the other organics tend to fall off. As I said, we're also monitoring the stiffness, and that's here on this plot on the right for different concentrations of our zinc oxide. And the stiffness, it's very, very compliant at the beginning. You know that from painting. And with time, we see the stiffness increase. So we want to be able to look at that in even longer times. And the way we do that is using a very small diamond. And we make what is known as a nano indentation in the material. And you can see in this micrograph here that we have a fragment of a piece of paint, and you can see that this diamond has been impressed in the paint. That gives us an indication not only of the hardness, But when we watch the whole experiment, it also tells us about the stiffness. And this probe here, this small diamond, is small enough that we can actually distinguish the properties from each layer in a given paint sample. If we were to look at the data here, now we're looking at these materials at longer times, and we're watching the stiffness as a function of time up into, this was done to about over 6,000 hours. We can change the atmosphere, we can change the temperature, we can change the humidity, and that is going to give us a key then in terms of treatment of these materials. So let's turn now to our second example, and that is the work of Matisse in this incredible painting of Bathers by the River. And what we want to, again, this is a technical art history study, what we want to view is what's the painting behind the painting. And there's quite a long history to this painting. Matisse actually started it in 1909. It was one of a series of 3 paintings that he was doing for a Russian collector, and the collector only wanted two of the 3. At that time, it was a very pastoral scene. In fact, what you see in this black and white photograph, here was the river. At that point, there was a river in the picture. You see there, the foliage there is quite different. The bodies originally of the folks around the river were quite soft and rounded. But by 1913, Matisse was getting interested in Cubism, and this painting began to change. And you can see that in evidence in late 1913. The legs here are becoming much squarer in places. There is a snake that has appeared into the picture as well. And because we have photographic records taken at the time by Eugene Drouet, we can learn a lot about what was the painting below the painting. So again, here is November 1913, and here's what we see at the Art Institute today. You'll see the foliage has changed. The river, which was in the center of the painting, has now become a black strip. So many, many changes. But here are the very, very important photographs that were taken at the time. We often use X-radiographs, much the same as you would get in a hospital. And so we can see the forms below the surface. But what we don't know is anything about color. And here's where some computer scientists, my former colleagues at Northwestern, Agalos Katsagalos, and Sotos Tafarias came into play to do this work, and because of their interest in colorization. And so they had the algorithms and knew how to do recolorization, but they were missing a very important piece. And working with conservators and conservation scientists and taking very, very small samples, what we're now able to do is merge 2 very important but different sources of information. So here is the paint fragment. This is the surface as we see today. If we go down a few layers, we see that Matisse's color palette changed drastically between 1909 and 1917. And by taking this information from samples at various parts of the painting, our computer scientists could put together, first of all, what we're seeing in the present day. Here is mid-November 1913, and based on their recolorized versions of the painting, we see the recolorized version from 1913. So you can see the changes. The form has changed, but not only the form, and the color has changed. If we look even further to the right in that painting, one might see something even drastic, more drastic in terms of the earlier version, where the very, very bright greens were used by Matisse in the earliest rendition of the painting. Okay, example number 3. And that has to do with, again, technical art history. And I love to describe this as 18th century nanotechnology. So if we look at this painting, this is a remarkable story. The gentleman on the right here is Augustus the Strong of Saxony. He had a penchant for Asian pottery, wasted a lot of money. I shouldn't say wasted, spent a lot of money. Spent a lot of money on bringing, I really didn't mean wasted at all, but spent a lot of money in bringing Asian pottery to Saxony. And he had heard about a character in the neighborhood called Johann Friedrich Büttger. Büttger was an alchemist. And ultimately, he came into the court of Augustus the Strong and became an indentured servant. The reason, of course, that Augustus wanted him there is because he needed more money to get the Asian porcelains into Saxony. Büttger was also a chemist. He was trained in chemistry. I guess that's the degree you really need to be a good alchemist. But he realized that he would probably have greater success discovering how to make high-quality porcelain than he would be trying to make gold. And that, in fact, is what he did. And this painting here has been labeled, Büttger shows Augustus the Strong the secrets of European porcelain. And so in Meissen, just in what's now Dresden, Germany, the Meissen porcelain manufactory was established. And Büttger, understanding that one needed high-quality raw materials and very high temperatures, was able to do this. The picture itself is a great example of what not to do at home. This is a crucible. You'll see that it's glowing, which means it's at least 600 centigrade, which means about 1,000 Fahrenheit. This is not how porcelain is made, but he's showing this to Augustus. Here's someone else in the workshop with a furnace. You'll note that he has bare skin around his knees, no safety glasses. None of our Caltech students would behave like this, okay? If you're interested in this, story, there is a wonderful book by Janet Gleason that I've pasted in here called The Arcanum. And it's a great story of industrial espionage and trademarks. In fact, it's my understanding that these porcelains were the first products to have trademarks. And although my family is rather embarrassed when I do so, oftentimes at nice dinners I will turn the china over to see what the trademark is. Okay. So let's now talk a little bit about Büttger, because we're not going to talk about the porcelain quite yet, but I want to show you a piece that was in the collection, that is in the collection at the Art Institute. It's this beautiful teapot. You'll see that in Meissen, they also would paint these beautiful Asian-inspired scenes on them. What I would like you to focus on is not the scene and not the gold painting, but the glaze here. the glaze that is between these gold markings that is now known as the Butker luster. And these were brown or pinkish purplish, very iridescent glazes. And so the question came to us, what comprises these Butker lusters? And again, we were fortunate to have a fragment. And we took this to the scanning transmission electron microscope. And what you see here is now a micrograph of this luster, and you see these beautiful nanoparticles. This is about 500 nanometers, and it would take many of your, at least, I want to say 30 or so of these particles to get something that would be the size of a strand of your hair. We also, in the microscope, have the ability to look at the chemistry. So we can not only see that these are nanoparticles, but we can determine what they are. And to no one's surprise, I guess, they were, of course, gold, because he was an alchemist. So we have these beautiful gold particles now that, depending on their size, will produce different colors. And this is science that is certainly well understood now. This was a great project, not the microscopy, but we had an undergraduate who was very interested in this, in doing the reverse engineering. Normally, we go at engineering problems by seeing how processing influences the structure and the properties, but here we're working backwards. We knew what the structure looked like. So from that structure, could we figure out how these glazes were made? And so Andy Asman here did this work. We recreated the recipe of a lead glaze and then used gold chloride that would have been available in the early 1700s and allowed that to diffuse in at high temperatures. And you'll see in Andy's glaze, we got a much pinker Butker luster, but which we could adjust by growing the gold particles a little bit larger. So we were able to reverse engineer that particular material. Okay, now to the question of provenance. So again, I'm going to talk about work that was done at Meissen, and just outside of Dresden. So again, this was in the Meissen manufactory. But we'll see here that a number of places around the world also worked on these red stoneware materials. In Delft, in China, the Yixing is certainly well known for this, Wedgwood in England, and Staffordshire. And all of these are made from clay. That clay is mixed with sand, and added to that is some sort of a fluxing agent to lower the melting point of some of the constituents. These are taken to high temperatures, maybe 1100 centigrade, that's over 2000 Fahrenheit, to form these. Now, these preceded the porcelains that I just showed in the previous example. As you might expect, there's a lot of iron oxide in that clay, and it was really the key, if we could get the iron oxide out, to get the purer clay for the porcelains. But these all contain iron oxide. And we had the very good fortune to be able to do a provenance confirmation with a series of 50 objects. So this was just a fantastic opportunity for us to have. So here are the objects. Some of them came from the Art Institute of Chicago. Some of them came from Sèvres in France, which is a very large ceramic museum, but was also another manufactory through the years. And some of them came from a private collector. And the provenance was largely 18th century Meissen that we were told. There were a few pieces that were 20th century Meissen. It turns out these were these commemorative coins shown down here at the lower lower portion of the photograph here, and some were Yixing, were Chinese. Each of these objects was examined. This is an X-ray fluorescence unit. You'll see that we can bring this very close to the object to collect the spectrum, and that spectrum is basically the fingerprint that tells us all of the chemical elements that are in the solid. Another piece of spectroscopic instrumentation is shown here, but I'm going to focus on this. And so let's have a look at what we found. So here are two pieces. One was in the private collection and one was at Sèvres. And we see they look identical. They look identical. Same handle, the surface relief, although the lighting here isn't quite so good, they look identical. And so the question was, are they both mycin? And so here, what I'm plotting here is all of the data that we've collected for some of the primary constituents in that red stoneware. On here, we're plotting the amount of titanium. On here, we're plotting the amount of iron. And this is in relative values. And what we see that's just terrific is that all of these samples now form a lovely cluster here. You'll notice that, not to our surprise, the 20th century mycin is off the charts here. That's to be expected. These green X's here had been attributed to Chinese red stoneware, and then there are a few others. So where are our teapots? They fall smack dab in the middle of this. And so we would expect that from that these two are indeed mycin. Okay? Here are another two teapots from all of the papers that had been collected on this. The one on the right here had been attributed to mycin, and on the left had been attributed to Yixing. And when they were analyzed chemically, it looked like they were also mycin. And in fact, to go a step further, some other elements, some of the trace elements were also examined to get a better sense of this, just to make sure that this wasn't happenstance, that it was still part, the teapot that was attributed to Yixing was not part of the Chinese group. And when that happens, again, now we're looking at rubidium, a minor element, and strontium, and we see them both, again, smack in the middle of this collection of data. So it looks as if, in fact, that Chinese teapot was misattributed to Yixing and really should be a part of the Butker collection. One last rather unfortunate examination is of this slop bowl. Again, this is from our private collector. It's a sad story when a piece in your private collection does indeed fall way out from the bounds of the mycin. So it has been really an interesting experience for me, seeing data that comes from a variety of different pieces, probably made within, 20 years or so, where we still can cluster data so closely to give us very important information on provenance. All right, we'll look at one more example, and that has to do with the Winslow Homer. This is for to be a farmer's boy. It dates to about 1887. Again, part of the Art Institute of Chicago collection. And in looking at it, it's rather curious. So here's this, the farmer's boy is looking over in that direction. We don't see anything there. The sky is just completely washed out. Although you'll notice that there are other objects in the foreground that are very rich in color. And in preparation for a large exhibit at the Art Institute, there were a number of studies made. And so I start with this photograph, and the question that I always think of is, why are these three women smiling? This one is smiling because she knows there are at least 28 Homer watercolors housed in the Art Institute. Actually, they ended up looking at about 50 of them because some came from the Philadelphia Museum and other museums. So they had just a wonderful collection of works to look at. This woman is smiling because what she has found is an 1887 reference book that contains the Winsor and Newton watercolors. And these were the paints that Winslow Homer used. This is a high school chemistry teacher, Lisa Backus, and she's smiling because this book was closed for many years. And it meant that these paints were not open to light or to the atmosphere that might do something to them. So what a great find that was. This is what happens if the book was open. So these are Carmine Lake pigments, and you see these very, very rich colors that after exposure to light long periods of time, they fade drastically, okay? Why does that happen? Well, let's talk about what are known as red lake pigments. First of all, they are coming from organic sources, like insects, shown here, and like plants. And one of the most famous is known, the dye stuff is actually called the cochineal, and the bug that produces this, I have to look at my notes here, it turns out that it takes 70,000 of these bugs to make a pound of cochineal red pigment, just so you know. When these dyes are highly fluorescent, the reason artists like them is that you only need a small amount of them to get very, very rich color. And it was then the intent of the folks at the Art Institute to begin to look for evidence of the red lake pigments. And we see here Christy Dahm at the Art Institute. This is how one experiment takes place. This is, again, another portable X-ray fluorescence unit. Basically, we're looking for elements. Here's one of the Homer watercolors here. And that's not going to give us the full story, though, just the chemical elements alone. Instead, we are more interested in the organic molecules that are produced when these insects are used to produce dyestuffs, or when these plants are used to produce dyestuffs. So let's move forward. So what technique then can one use? And the technique that we took advantage of, actually my Northwestern colleague in chemistry, Rick Van Dyne, is an expert in what's known as surface enhanced Raman spectroscopy. Let me tell you a little bit how that works. Here is a molecule, and it's sitting on a nano-patterned surface. And this is excited by a laser, and from that there is a scattering from this molecule. The absolute wonderful thing that happens with this scattering is that one gets enhancement of that scattering signal by 10 to the 5th to 10 to the 7th times. What that means is that we can get the information necessary to identify a molecule having only a single molecule there. So we don't need much sample at all, okay? So it's just a fantastic advantage for this type of study. So just to give you a sense of how well this works, here is one of the red lake pigment molecules. This is purpurine. And here is our signature. This is our fingerprint of purpurine. This is what we would get if we use standard Raman spectroscopy. This is what we get from the surface-enhanced variety of it. So it is an incredible, powerful technique to be able to identify these dyes. Okay? So now let's go back for to be a farmer's boy. Okay? Here we are. This is just a close-up of the boy looking at the washed-out sky. And here is a magnified view of a portion of the paper. And what you notice here is there is some pigment still there. And in fact, by virtue of the structure of paper, if you've ever looked at it up close, you know that it's a series of fibers. And if one is careful enough, you can go in with a little scalpel, you could go in with some sort of a needle, and from that, get something that was underneath one of those paper fibers. And from that, get it to the point where we can get it to our spectrometer and identify it. And so here is just a microscope view of some of the particles that could have been taken from the paper and then transferred to the surface-enhanced Raman spectroscopy. And here we see on the right the various spectra that were identified from these pigment particles. What this has meant, or I should say, the analysis of these has shown us that in this particular painting, there was both red and yellow pigment in the sky. So what might that look like? Here we see the current version, and here is the virtual restoration. And I think we now understand what the former farmer's boy is looking at. So he's looking at the sunset. And so had you been around in 1887, this is what you may have seen at a Winslow Homer show. Before I end, I want to talk about one more aspect of all of this that was completely unintended when we began this partnership and collaboration more than a dozen years ago. And that is the fact that art is a powerful tool to be able to bring people to science. And we learned this from one of the high school teachers who spent a summer with us. In fact, it was Lisa Bacchus, whose picture you saw a little earlier. Spending the summer with us, one of her obligations as in a program called Research Experience for Teachers was to come up with a unit to take back to her high school. And Lisa she knew she had to teach chemistry to the students who didn't want to take chemistry. And so by the end of the summer, she had put together this phenomenal unit to do that and said, I'm going to go in, we're going to make our own pigments, we're going to make our own paints. And once we do that, we're going to ask the question, why is red paint red? And use that opportunity to then talk about light and absorption and reflection waves and atoms and electrons and energy levels and chemical bonds, and explain to her students why this is red and why the hat in The Two Sisters on the Terrace is red as well. She also went further and said, how many art techniques can we describe that have engineering underpinnings? And I show that here. I'm sure her students did some sun printing, and then back in the classroom, she showed them how that is related to photolithography. So this was completely unexpected when we started, but has certainly given me pause to think about how I can take my work in this for various outreach experiences. So to close, I just want to show you that there were a lot of people involved in these 5 examples. I've had the pleasure and privilege of working with some wonderful folks at the Art Institute of Chicago, at Argonne National Laboratory. When we did all the Meissen work, we had wonderful folks to work with in Paris and at the Sèvres Museum. And of course, Lisa Backus as our high school teacher. So with that, I will close. I'm happy to answer questions for you this evening. I think there are mics here that we can use. But thank you for your attention.